Hello, folks. We want to continue talking about vectors actually. In the past, we have learned about geometric vectors. A geometric vector is nothing but a representation of a vector using an arrow diagram or using a directed line segment. Um, we know that a vector is a quantity that has magnitude, unit of measurement, and direction. So this is one example of a vector. This is a geometric vector, vector AB. It makes an angle of 62 degrees with the horizontal. So we use the vector symbol, which is the arrow on top of AB, and we say 5.2, that's the magnitude of the vector. Kilometers is a unit of measurement. And the quarter bearing here, it says east 62 degrees north. So this is how you represent a geometric vector. So we have learned about this. This might be a displacement vector. We have worked with velocity vectors, force vectors, and so on and so forth. So geometric vector we are somewhat familiar with. But now we want to learn another representation of the vectors. It's called Cartesian or algebraic vector. Now, why we call it Cartesian vector? Because we are using coordinates of points in the Cartesian plane to represent those vectors. So I have a vector here, vector OP, and it has a tail located at the origin. The coordinates of the origin, needless to say, it's 0, 0, and coordinates of the tip of the vector is 8, 6. And the way we show this in Cartesian vector form or algebraic form is by using square brackets. So vector OP equals, this is an ordered pair. We use square brackets, 8, 6, and 8 and 6 show the horizontal and vertical components of this vector. So the horizontal component of this vector OP would be a vector like this. That would be like vector OB, let's say, okay? And then the vertical component would be vector BP. And when you add vector OB with vector BP, of course you get vector OP. That's the triangle law. So we are using the horizontal and vertical components of vector OP to show that. What is the horizontal component of vector OP? Well, it's vector OB, whose magnitude is 8 units on the x-axis. What is the vertical component of vector OP? It is vector BP, actually, which is 6 units on the y-axis. So 8, 6 is the ordered pair that represents a Cartesian form or algebraic form of this vector OP. The tail of the vector may not necessarily be at the origin. So if I translate this whole vector, let's say 3 units to the left, so I'm going to end up with -3 right here, and 1, 2, 3. If I move 3 units to the left, I'm going to end up with a vector like this, okay? I'm going to call this vector CD, okay? Now this vector CD is in the same direction as vector OP. It has the same magnitude, it has the same size. Everything is the same except that the location is different. So vector CD in general is just a Cartesian vector. It's a algebraic vector. But vector OP in particular, only because its tail is specifically located at the origin, that's why we call this a position vector. So any point on the plane can have a position vector. And simply to find the position vector of any point in a Cartesian plane, you just connect the origin to that point, and that will be the position vector of that point. And obviously, position vector is like a special case of an algebraic or Cartesian vector. So position vector, always remember, has its tail located at the origin only. Okay, so vector OP, we talked about it. And we said that vector OP and vector CD are equivalent vectors. They are equal vectors. They have the same direction, they have the same magnitude, the size and everything is the same. Okay, but vector OP is called position vector only because its tail is located at the origin specifically. Okay, so now what happens? Oh, by the way, some textbooks they're using regular brackets to show the Cartesian vectors, but luckily our textbook is using square brackets, which is a very good thing because at least there is a way to distinguish between coordinates of a point and a vector in algebraic form. If you put regular brackets in the context, you may know that it's a vector, but it may be confusing because people might think that that's the coordinates of a point we talk about. So we will always use square brackets to show algebraic vectors in our course. Okay, so now what happens if I double the size of this vector? Okay, so if you double the size of this vector, you end up with a vector which would be larger. So vector OT has the same direction, but its magnitude or size is double the size of vector OP. So vector OT is 2 times vector OP. So what do you do when you multiply an algebraic vector by a constant, let's say k in general, in this case 2? Well, you multiply the constant by every single component because not only the horizontal component of vector OP has been enlarged or has been doubled or has increased, but also the vertical component has been doubled and increased. So 2 times 8 is 16, 2 times 6 is 12, and that will be the algebraic vector OT in Cartesian form. Okay, so generally speaking, if you have a k, a real number, and you want to multiply that k by any vector u, and that vector u has components of u1, u2, you have to multiply k by every single component. So it will become ku1 and ku2. Okay, so if k is negative, of course, then the direction of the vector is going to change. Because if I multiply vector OP by -2, then the direction would not be up to the right. It would be down to the left, actually, right? Because of the negative value of k. In this case, it's as it is. And if it is 0, then I will end up with the 0 vector if k is 0. Okay, so multiplying a scalar by a vector in algebraic form, that's how you do it. I'm talking about operations with vectors. How do you add vectors? So we have a vector 1, 2 and another vector 11, 10. Okay, I want to add the 2 vectors. Okay, you add the horizontal components together and you add the vertical components together. As simple as that. So you end up with 1 plus 11 and 2 plus 10, which is 12, 12. All right. And how do you subtract vectors? It's very easy, actually. So whoever came up with the idea of Cartesian vectors, algebraic vectors, that was a good thing because it simplifies our job. If we want to subtract 2 vectors or add 2 vectors in the geometric form, it will be a lot of work. But right now, you see that how easy it is to use algebra to add or subtract vectors. So 6 and 8 minus 1 and -4. So you go 6 minus 1 and 8 minus 3. So that will be 5 and 11. So that's how you easily subtract or add 2 vectors in algebraic form. Magnitude. How do you calculate the magnitude of a vector? Same vector I had, vector OP. I want to find the size of that vector, let's say. So it's not difficult to find the length of the hypotenuse using Pythagorean theorem. So I'm going to say the magnitude of vector OP using the symbols for the magnitude is going to be the square root of 1 leg of the right angle squared plus the square of the other leg of the right angle triangle, following Pythagorean theorem. No secret here. So it's going to be 8 squared plus 6 squared, and that will be, of course, 10. So we see that the magnitude of vector OP is simply 10, and I used Pythagorean theorem to find that. Now, if we have a vector in general, like vector u, with coordinates of u1 and u2, then the magnitude of that vector in general, to expand the idea, will be found with u1 squared plus u2 squared. And that is very obvious. It comes from the Pythagorean theorem. You square the horizontal component, you square the vertical component, add them up, take the square root. That will be the magnitude or the size of the vector u, whose components are u1 and u sub 2. Okay, so magnitude of a vector, operations with vectors, we talked about it. And now in a unit vector, on the x and y axis, there are vectors whose magnitude is actually only equal to 1 unit. See this vector here, for example, and this vector here, they're small. I can draw them larger. So this is a vector 1, 0, 1, 0. It's on the x-axis. The other one is 0, 1. It's on the y-axis. These are called unit vectors along x and y axis, and they have special names. This one is called I hat. I hat. Okay, that's the symbol we use for unit vectors. And this one is j hat. So j hat is the unit vector along the y-axis. I hat is the unit vector along the x-axis. And I should use here, actually, I should use square brackets, because at the end of the day, these are vectors. It is true that there are unit vectors. It is true that their magnitude is 1 unit, but at the end of the day, they are vectors. Okay? And speaking of operations with vectors, you can use these unit vectors to do operations with vectors. Now, this same vector here, I hat, can be written as u1 times I hat plus u2 times j hat. So you can express any Cartesian vector in terms of the unit vectors along x and y axis, basically. So let's say you have the same thing, 6 I hat plus 8 j hat. This is the first vector, minus 1 I hat minus 3 j hat. So I'm writing the Cartesian vectors in terms of unit vectors I and j, and then I'm subtracting them. So I get 6 I hat minus I hat plus 8 j hat plus 3 j hat. Okay, because minus is plus. So 6 I hat minus 1 I hat, that will be 5 I hat, because imagine you have a vector along the x-axis, which is 6 times the length of unit vector I hat, and then you subtract 1 times vector I hat. So that will be 5 I hat, and then plus 11 j hat. And you see that it's the same answer that we got before in the Cartesian form. So that's how you can work with unit vectors. Now, the only other thing that maybe I have to mention is that how do you find a unit vector along the given vector OP? Like, let's say we want to find this unit vector, something like that. I call it u hat. Okay, so u hat is the unit vector along a given vector u. It's very easy. It's very logical, actually. If the size of vector OP is like 10 units or whatever, if I divide the vector by 10, then its size will become 1, obviously. And that's what I'm looking for, a unit vector whose magnitude is 1. So all we're going to do in order to find the unit vector in the direction of a given vector is by dividing that vector by its magnitude. And when you're dividing by magnitude, you're dividing by a number. Let's say you divide by 4. And when you're dividing something by 4, it means you're multiplying it by 1 over 4. a quarter, in other words. So I'm going to come up with this formula that u hat, which is the unit vector along any given vector u, would be the vector itself divided by its magnitude. Okay? So this becomes a formula for the unit vector along any given vector u. U hat stands for unit vector along vector u. Vector u is the vector itself, and magnitude of vector u is the size of that. And you can rewrite this actually as 1 over magnitude of u hat times the vector, and that itself could be written as 1 over square root of u1 squared plus u2 squared. Okay, that was the magnitude of the vector. Okay, and then times the vector u1 comma u2 itself. So you can write it in a variety of forms basically, but formulas don't change, the concepts do not change. All right. So this would be like a formula for the unit vector along a given vector. So let me do the unit vector for this same example. So I have space here. I'll say u hat equals u divided by its magnitude. So vector u was vector OP, which was 8, 6, and I divided by 10 because I found the magnitude earlier, right? So the answer would be 0.8, 0.6. So this is the unit vector along the directional vector OP or vector u. Okay, now those who don't believe that the size of this vector is actually 1, why don't you grab 0.6, square it, 0.8, square it, add them up, take the square root, it will be equal to 1. If not, then contact me. Okay, so the magnitude of this unit vector will definitely be equal to 1. Thank you for your information. I think I covered what I wanted, although every second counts. It's very hard, to finish up all the things you want to talk about in like very short period of time. But I'm doing my best as you do your best. Okay, thank you very much.